more detail into what we're going to be talking about. So we're talking about the 3 projects. We're going to talk about how those projects actually went, both the good and the bad, how they played out. We focused on smaller, simpler projects. We don't want to give you the impression we don't do large projects. So we've done massive projects, but they don't lend themselves to talking about in a 30-minute webinar. And then one last thing we're not going to really talk about are some of the client names of these pictures we're going to be looking at in projects. We do have permission to talk about the projects. We don't always get permission to specifically say who the client was. We're just going to jump right into the first project today, which is a vibration chamber at the NASA Space Flight Facility down in Ohio. Very, very interesting facility, a lot of history to it. The overall scope was to scan really less than 10,000 square feet of a pit. The pit essentially has a large isolation table in the middle of it, or vibration table in the middle of it. That table, they place actual rocket components on and simulate re-entry by shaking them. What they needed from the model was the ability to compare it to what they had in CAD, their plans that they knew were out of date, and verify they would be able to fit all the structures needed to basically contain a rocket engine that would tip over. For that purpose, our final output was just going to be a step model, a 3D model of a step file, along with the native point clouds and other formats. Overall, for the project, came in just under $4,000. So for the actual data acquisition on site, it took us about 3 hours of travel time, round trip, a little less than 4 hours of scanning, and we chose to do it in color even though it wasn't contractually required. We were able to pretty easily complete the model, although it turned out to be a little more complex than maybe we thought it would be at first. It took us about 48 hours of modeling time. So some of the details on it, the challenges first off, it was a octagonal pit, 8-sided, and the piping, lots of piping and other items in the pit, and they did not run parallel or even perpendicular to the walls of the pit. Over time, things have been added. Things were not square. Anyone that's worked in modeling knows that can be a little tricky to accommodate. The other thing we ran into was a lot of custom components. A lot of the modeling we do, we have huge standard libraries for now that have been developed over the years. Very little of those libraries apply to this project. Almost every piece had been fabricated on site. And so it's kind of the outcome of the project. We were able to deliver the model on time, even though it was difficult to model, a lot of custom components, like I said, but we still hit the deadline. The client was easily able to import it into the PTC Creo, and they were able to then successfully use it to test for the next the future program that was coming. So for each one of our 3 projects, I think it's important to also look at the alternative had we not scanned. Because this is really the benchmark of why we scan. Amongst other things, scanning being more accurate and more complete, it's also scanning needs to be cost effective. So on this one, we based it on our experience. We've also done a lot of manual field checking over the years and have a pretty good idea of what this would take us to manually check this project. So most of the savings on this is going to come in from the actual manually measuring versus scanning in the field. We were able to scan this whole facility in less than 4 hours. We estimate, given the complexity, this would have taken at least 48 hours to manually field check in the field, a little over a week for one person. Combine that with the modeling. Modeling was probably a little simpler on this one with the scan versus from manual field checks. And we end up with basically 50 hours compared to an estimated 80 hours had it been manually field checked and modeled. Move right on to our second project. This one is well, it's to be honest, it's the most difficult project I've ever done in over 15 years of working in the scanning business. The density of equipment we ran into on here is really like nothing I'd have ever encountered before. From start to end of this work cell, it was solid equipment. In some cases, we were running a scan every 12 inches just in order to visually capture all the information. To go into the scope a little bit on it, this is, like I said, it's an automotive assembly shop. In particular, this is a cell where the upper and lower parts of a car come together, where the engine, transmission, brake lines, axles, everything gets stuffed into the body of the car. The purpose, from the client's perspective, of why we were out here doing this is they had new tooling and existing tooling that was being kitted. The new tooling was going to be a very tight fit. They knew that going into this. This is also has turned out to be one of their most difficult projects they've worked on. We ended up, the final amount we charged for this project was $9,300. That is not what we would charge to do this project again, but that's how some of them work out. So for the scan, we had about 2 hours of travel time round trip. We were out on site for about 8 hours, a little over that, and in that time we did around 160 scans. With the model, here's where we really kind of ran into some trouble. We ended up going well over 400 hours to complete the model, given the incredible complexity we saw. So the challenges, like I said, this is the most complex, densely packed equipment I've ever encountered. It has, I believe we were told, this particular cell has been around for around 20 years, and over that time has just become more and more densely packed with equipment. And the reality is, from the client's perspective, manually field checking this was probably not an option, even though in a minute here we're going to talk a little bit about what we project those hours would have been to manually check it, but you would have ended up with a very different deliverable, far less all-inclusive than what we provided. To the outcome, we did deliver the project. It was not on time in this case, unfortunately. But the client, very understanding, they were also having challenges on their end given the complexity of the project. The model did provide a lot of value to them, though. They were able to identify many conflicts they wouldn't have known about and take proactive action to correct those in their fabrication shop versus traditionally they would have had to be field fitted. We don't actually know the final outcome of this because the final tooling, some of it will be going in the next few weeks. Other parts of it won't be arriving, I believe, till March. Let's talk a little on kind of how we project this could have been done manually. Like I said, this would have been a very different project had it been done manually. It would have been far less detailed, far more generic of a layout. But we think you probably could have had something usable in around 440 hours versus a little over 400 that it took us to complete the project. Okay, with that, I think we're staying pretty close on time to get everyone out of here in about 30 minutes. So we're right into the third project. This one is reverse engineering for plant maintenance. So in this case, we have a client whose goals, they were responsible for replacing wear components on overhead power and free conveyors. These are the riding bars that serve different purposes. Some of them simply stabilize large overhead carriers in automotive plants. Some actually have far more wear because they're actually using as pressure to drive the carriers open for decking the vehicles onto other conveyor systems. These are very complex geometry because they have to follow the path of the conveyor in a way that keeps it stable, and over the years have been very much field fitted. So the output from this was going to be used in UGNX through a step file. And the average, we did multiples of these jobs. They started in the over 5,000 range, and now we're getting them down to sub 4,000 range, just as we've gotten more comfortable with exactly what kind of output the client needs. So for the scan, we're completing the scan in about 2 hours, or 2 hours of travel time, and then 2 hours of scanning time. In that time, we're doing around 24 scans. Just in general, maybe to touch on this, because these numbers are a little all over the map, our target is around 30 scans per hour, but we don't always achieve that. And on smaller jobs, that's much harder to achieve. There's a certain overhead involved in simply getting in and out of these facilities, carrying equipment around. So in this one, you see we were there for 2 hours. We did 24 scans. The reality is we were really running the scanner for probably a little less than an hour. Another hour and change was going through security, watching plant safety videos, being escorted in. And here you can start to get a feel for just how complex the geometry is on the load bars or the riding rails. These are definitely field fitted, and over time have been slightly adjusted to make sure that the carrier behaves in the way the plant needs. So, I guess in general, 60 hours is about what these projects take to do from a modeling perspective. That's because they require us to do a lot of individual cross-sections through the conveyor system to ensure we're following the path exactly and produce the ultimate output the client needs. We already covered some of the challenges, very complex overhead systems. They needed a very fast turnaround time. In general, these are completed from the time we scan to the time the model is delivered is less than a week. Stabilizer track in general, it's not just complex, but it requires a high level of precision to ensure that these conveyors don't rock back and forth, the carriers don't rock back and forth. The outcome, like I said, we've done multiples of these projects now. Each one has gotten progressively better, faster, cheaper, which is exactly what we want to see. And overall, the client's been extremely happy. They're now able to, on the first project, they didn't totally trust us, and they sent a lot of field personnel to make sure it would go in well. By the third or fourth project now, they're pretty much fabricating the stuff off-site, and it's simply fitting into place within the plant. So here again, we're going to talk a little bit about hours. Now it's important to mention that these again are estimates, because what we're producing with scanning simply cannot be produced with a manual field check. It's not realistic to think you could get the level of detail and the precise measurements that we generate from scanning through any form of manual measurement. So in this one, we're estimating that this would take around 24 hours to manually check this. It would also require additional safety personnel and sending people up in man lifts in order to access the conveyor and take measurements. On top of that, from the modeling perspective, we think it would take about the same amount of time to model from manual versus from the scan. That's an important topic to bring up. We think on some projects it's a little faster to model for manual field checking. Never by very much, but sometimes it can be a little faster, especially when you're talking complex tooling. But when you're talking things like this, it's going to work out to be about the same for modeling.